to apply this form, okay, and then we will resolve that issue. But I think I have a better technique. Okay, this one is what I mean here. We look at this form, and what this form is saying is what I apply here. So basically, here I try to demonstrate is to apply this rule to you, and how can I do it? So again, let me try to demonstrate this one. So here for our Fs is what we want to convert is S plus 1 cubed, this one. Okay, we want to find the Laplace inverse of this term. And either you can apply this formula directly, okay, but in my my personal kind of calculation, I always apply this one because that would be easier. So for example, for this case, then here again the Fs equal to this, and basically this one is equivalent to we have this form, and when we set up as replaced by S plus 1. Okay, you can think about it like this. And so right now, this form basically is this one here. And for this one, we take the inverse Laplace transform has this form. So that means per our formulas here, f of s, and then for example, when we replace s by using that formula here, then the inverse Laplace transform per the that is e at of ft, the lowercase ft. So we do this one. So right now our f of s is this one here. So for f of s, for this one, if this is the f of s is the ft, by this one you can see for when s equal to n equal to 2, then we have this form that is t squared divided by 2. Again, we take up this formula when n equal to 2, basically this is s cubed, and multiply 2, and so that means the 1 over s3 have the inverse of Laplace transform like this. So right now we have taken care of this one with this one, so that means equivalent to our example is this one. And right now per our formulation we need to take up this one, so this one will also multiply with e of at. A is here, for our example, A is minus 1. So that is what I did. Okay, so here I basically show you is either you can try to take up these formulas or you can directly make a map to the tables here. Okay, so we're back to the, and for that one, I don't, so for the second term is how much? The s squared. For the second term is s plus 1 squared. And what is the coefficient? Do I have that one? Whatever, let me use the d2, okay? So for this one, the inverse Laplace transform of this one basically will be equal to d2 multiply, and again, we apply the rules one more time. So that is the, basically that is the multiply with the inverse. So basically this one, inverse of s plus 1 squared. Okay, so for this one, that is equivalent to s squared when we replace s by s plus 1. So now the inverse of this one will become, again, this take the Laplace inverse will become is this 1 of s squared. You look up this here is t. So basically that is t. And then again, we have to take care of this form because right now we taking up this this format in e minus 8e over 8t. So that is e minus t here. So this whole thing will become is d2 times e minus t times t. Okay. Okay, so that is this term here. And then for this one, that is very straightforward. Basically, the 1 over s plus 1 basically equal to e minus 8t, e minus t. Okay, so that is this term. And multiply with this coefficient. And 1 over s, the Laplace inverse simply is a constant 1 here. Okay, so here, after we have those things, then the last step, and again, term by term, individually look up the tables. Hopefully you can find the correct terms and mapping into it. This is the, for this, and this is the exercise to show you, say, if we have differential equations. These differential equations, for example, represent the single degree vibration systems on the forced vibrations. Okay, and or this can be a representation of the RLC circuit, the resistance, capacitance, inductance, and under the force oscillations. Okay, and or if you want to continue, this can be the thermal systems. Thermal system. This can be usually most of the thermal systems are the first degree. It's not second degree. But anyhow, okay. So this can be any kind of a system like this. So if our goal is we want to solve for y of t. So let me write up here. Let me get on the slides. Okay, so here is the Laplace, say y double dot, and let me write it up here, is s squared. So for example, we define the Laplace of y of t, let me say that is y over s, okay, by using these definitions. So here, this Laplace transform will be y limits of s minus s times y dot 0 minus y 0, and then y dot is equal to s y over s minus y 0. So with those things, we simply plug in here. So double dot is this one, s squared. And let me here, okay, so minus s y minus y 0, and plus 4. Right now I'm working on this one. That is s y over s minus y 0, and plus 3. Right now I'm working on this one, so that is y over s. So here is equal to Laplace of e over t equal to, what is this? Anyone? Do you have
1 over s plus 1?
Printed?
1 over s plus 1?
Minus 1, right?
Oh, minus 1.
Okay. So here this term is s minus 1. So right now we have the whole thing. Let me first collect the terms regarding this one. Yes.
Isn't the minus sy minus y dot not?
The first term.
Oh,
Yeah.
sorry.
So you need to change it on the other side too.
Yes. My mistake. Okay, so let me collect this term. So basically y over s and the coefficient of y over s will be equal to s squared plus 4s plus 3. So you can see for this one, the coefficient 1, 4, 3 basically is the same as 1, 4, 3. Okay, so that provides you as a checkpoint. And the remaining, let me collect the initial conditions. So here we have, we simply plug in the conditions now. Okay, so this y 0, so this one is 0 is gone, this is 0 is gone. So here we only have is minus y dot 0, so minus 2 equal to s minus 1 here. So therefore here do one more term, and so here let me skip okay, s squared 4s plus 3, and y over s equal to s minus 1 plus 2. Is that right? So this one will continue, this will be equal to s minus 1 and then s plus 1, right? 2, no, 2s minus 1. So therefore, y of s will be equal to s minus 1 and s squared plus 4s plus 3, 2s minus 1. This one, right now, again, we can factorize the whole things. For this term, if you look at this carefully, this one basically equal to 2s minus 1, s minus 1. This one basically is s plus 1, s plus 3. Okay, so from here we can factorize into a few terms here. So that will be equal to s minus 1 and s plus 1b and s plus 3c. So here let me not repeat the whole calculation. I think for this example, the calculation of ABC should be very straightforward. Okay, so here we can find out the A would be equal to 1/8, and B equal to 3/4, C equal to minus 7/8. So therefore, from here we can calculate y over t simply is the inverse of Laplace transform of y over s. And that means here is the inverse Laplace transform of the A term 1/8, 1s minus 1. And inverse the B term 3/4 and s plus 1 and minus 7, 8 inverse Laplace and 1 s plus 3. Okay, so basically that is 1/8. This one, if you look at this, look at the table, is exponent t, and this one 3/4 and minus t, and the last one is 7/8 and minus 3t. So this is the response of the system and in the time domain. And right away you can tell the system eventually will blow up, because for this case this is exponential growing. So if this is a time exponential growing, and this one is exponentially decaying like this. For this one, exponent 3t is even decay even faster. Okay. Due to this term, so when time goes by, the yt, whatever the y, for example, if y represents a displacement, then the system's displacement will go perpetually from its equilibrium positions. So I can tell the system due to this excitation is unstable. Yeah, here is our exercise, using shifting theory. For example, if we know, and say we know the cosine, the Laplace transform is this form. So, for example, if you pre-multiply this cosine with certain exponential functions, then its Laplace transform simply is this. The first, you work on the generic template on this, and whenever you multiply in the time domain with exponent functions, then equivalently you work on in the x function is you simply replace s equal to s minus a. Here if it's positive a, here is minus a. So for example, here for this example here we simply replace it like this. So exercise of this can be let me make up one. So say sine bt. Okay. So again, the sine bt, the Laplace transform is s squared plus b squared b. Okay. If you look at the tables, that should be like this, and right? Okay. So now, for example, if in the time domain, you're working on the signal is like this, say the AD sine times BT. So this is providing us your template. So for this one, the Laplace transform is this. You take whatever the template from the generic form, and then you replace s by this one, s minus a. So basically the result is b s minus a squared plus b squared. Okay? And examples is this. And let me make up one. Okay? So say earlier we have tried is s squared plus 4s plus 3. For this one, we know this can be factorized into this. And this one either further can be written up like this. trust me. Okay, double check. Double check. Okay. So therefore, for this case, the inverse of this term is equal to here 1/2 exponent minus t and 1/2 exponent minus 3t. And again, here I have utilized is exponent inverse s plus a equal to minus at. I have utilized these properties for this. So for this case, we can factorize this piece of cake. And now we try the other example here. For example, we consider the same s squared plus 4s and plus 5. Okay, we change a little bit here. And by all means, this one you won't be able to factorize into this. And if you want to do the normal way, you might, I think in our homework, the last questions, and have a similar problem like this. And I think the if you as a beginner, you might try as I did before is I try to resolve what is the root of this. And say, for example, if the two roots are, say, as here I'm kind of writing the script, you don't need to write, just listen. Okay. Right now I'm showing is the not an inappropriate process. So say if the two roots are, say the two roots are P1 and S plus P2. So what is the roots? Let me try to find it. The roots P1, P2 are equal to 2a minus b plus minus 2a b squared minus 4ac. So this one you might come up with is 2 minus 4 minus plus 4 2i. So that is minus 2 plus I. So for this case, you might come up with is this s plus the s minus 2 plus I and s minus 2 minus I, right? We don't have a Laplace transform tables for complex numbers. We don't have, unfortunately. Okay, and so if you like to try this way, you start there. And so what you can do, so this won't work. So the way you can try is apply the shifting theory. The concept is try to rewrite the denominator in a way of combination of something like this.
So by completing the
Yeah,
square.
something like this one. Make a one square term and then the other is remaining. So here, let me do this one. So here can be, you can do like this: s squared plus 4s plus 4 plus 1. And I know this one can be s plus 2 squared plus 1, right? If you like, you can put into right format. Here you can say 1 squared, either way. How about let me make extreme examples here. Let me say this is 6. How about that? So here should be equal to square 2 squared. Okay? Look at this one. Right now, this one is actually fitting to where? Something like this. You can see this term has been very close to this one. Very close, not identical yet. So, but to there, so maybe we can rewrite this one. Here we have to do is to, you can see for this term, the b here. So you have to rewrite this one as a square 2. How can we do it? You simply multiply square 2 divided by square 2. Okay, pre-multiply and divide it. That's it. So once you have this one and you know this form, so basically the inverse of this one, simply look at this one. So that will be equal to 1 square, 1 over square 2, and then we'll look at this one. So we have those, we simply mark to here carefully. right now A equal to how much? A equal to -2 and sine square 2t. Are we okay? For this signal, let me draw it. The signal will look like this. This is t, and whatever, let me call that function. Let me call the function. So this function basically is a sinusoidal function, and the sinusoidal function basically is oscillated in an envelope defined by this. So this is the profile. This profile is e minus 2t. Oscillation of the sine. So this is the sine, and this is sine square 2t and multiply with whatever the coefficient here. Okay, and square 2. So for this system is oscillating, but also the oscillation is decaying, defined by this profile. So this system will eventually converge to 0.